Hi, my name is Dheeraj Chahal and I am scientist with TCS Computing Systems Research Lab. So today I'm going to talk about our work on high performance serverless architecture for deep learning workflows. My co-authors in this work are Manju Ramesh, Ravi Ojha, Rekha Singhal. I will start my presentation with the motivation behind this work and our objective. We'll discuss the use case that we have used for this study, which is an invoice processing application called Deep Reader. We'll discuss in detail the methodology that we have used for migrating this workload to AWS serverless platform called Lambda. We have conducted some experiments and we'll discuss those experiments in detail, where we'll talk about the cost and performance trade-offs involved in serverless architecture. And then we will conclude. We all know that when it comes to deep learning model inference, there are very stringent service level agreements that one is supposed to honor. So these agreements talk about the minimum throughput that is expected and the maximum allowed latency for the inference request. Now, in order to honor these SLAs, apart from optimizing the application, organizations also arrange for very high performance clusters, which incur very high cost because upfront investment is required. And sometimes this solution is not economically viable. In order to provide cost-effective solutions, organizations are looking towards the cloud deployment, and they're migrating their workloads to cloud. In fact, cloud vendors provide multiple solutions for deploying especially the AI workloads. So serverless computing platform is one such architecture which is emerging as a popular paradigm, especially for event-driven artificial intelligence workloads. And almost all popular cloud vendors, they provide serverless computing platforms. For example, Amazon provides AWS Lambda, Microsoft offers Azure Functions, Google Cloud provides Google Functions, and IBM provides OpenWhisk. There are many advantages associated with the serverless architecture. First and foremost is high scalability. So as the workload increases, user can spawn new instances immediately. And then it's very cost effective because of its pay per use model. So user is supposed to pay only for the duration when the instance is actually used. And it provides location independence because these vendors offer instances in multiple geographies, so a user can choose instances close to its location. And it also offers minimum operational logic, such as there is no need to worry about the operating system because it is provided as function as a service. So with this motivation, objective of this work is to discuss the challenges and also talk about the solutions for migrating large deep learning model based applications from on-prem deployment to the serverless architecture on cloud. We'll also discuss the architecture for deploying such application using multiple cloud services, which includes the storage like S3, file systems like EFS. And then we'll talk about the performance and cost trade-offs while deploying these deep learning model based applications to serverless architecture platform. And we'll compare the serverless platform with the on-premise deployment in terms of the performance and the cost involved. In this work, we have used in-house application called DeepReader. It's an invoice processing application built with the composition of a number of APIs. These APIs implement state-of-the-art vision algorithm and contain pre-trained large deep learning models. The application logic performs the data extraction as well as transformation. And there are multiple workflows in the application to process images from different classes. Each workflow consists of one or more application APIs. The important APIs in the application include the optical read character recognition OCR API for reading characters, words, and sentences, along with the coordinates extractor API for detecting semantic data types of the words, and table detection API for identifying the tables in the images or PDF document. Apart from this, there is relationship extractor API for identifying the relationship that exists among the different entities in the document. Amongst all the APIs that I just talked about, OCR API is the most frequently used API, and the two major steps in this API are text detection to find out where the text is present, and text recognition to identify the words. And we use CTPN model for text detection and TextRect engine for recognition. As you can see in the figure, for better accuracy in CTPN inference, the input image is split into multiple slices with overlapping regions. Each slice is given as the input to the CTPN model as shown in the figure, and it provides bounding box coordinates of the region where the text is present. The overlapping boxes are combined, and the batch of unique polygon containing text is then sent to TextRect engine for recognizing the text. The sentences and the text blocks mapped to their coordinates is the final output of the OCR API that is returned as the JSON and consumed by other APIs. Let's talk about migration of deep learning application to serverless architecture and see how OCR API is deployed on AWS Lambda. An event is triggered when the image is uploaded in the S3 bucket. The event notification from S3 results in image processing by OCR Lambda function containing the OCR API. The OCR function slices the image into multiple parts and stores them in EFS. The image slices generated by OCR function are consumed by equal number of CTPN instances. The CTPN Lambda function process slices in parallel, and generated files are returned back to the OCR for further processing by TextRect engine, and this is happening through EFS. A Lambda layer is created with the compiled binaries and configuration files. This is then imported in OCR main Lambda function. There are a few important things to note here, such as that AWS services used in this architecture are placed in one virtual private cloud VPC. Also, files shared among OCR and CTPN Lambda functions are put in EFS, while all other files that are required are saved in temporary storage /temp of the respective lambdas. Also, the final output generated by OCR API is stored in separate S3 bucket. Apart from the advantages that serverless platform offers, there are certain disadvantages as well. For example, AWS Lambda has only 500 MB of temporary storage available, and it allows only 250 MB of memory for package deployment. And the deep reader application that we are using contains very large deep learning models along with the framework and libraries. So it uses CTPN, which is around 270 MB in size, and also uses TensorFlow, which is further 220 MB in size. So in order to fit these frameworks, libraries and packages into AWS, there are certain optimizations that we have applied. So what we have done is we have trimmed some of the components from TensorFlow, like we removed TensorBoard before we deploy it on Lambda, and some of the libraries that are not required by our application, those libraries were eliminated. After doing this exercise, we could reduce the total size by 50%, and it was easy to migrate. And also the TextRect engine and OpenCV model that we are using in this application are loaded in Lambda layers, which can be shared across multiple Lambda functions. One more constraint with serverless platform is that it is stateless in nature. So to load the CTPN model and to save the intermediary files that are generated during the processing of the images, we have two options available. We can use either EFS or S3. In our implementation, we are using EFS because it offers low latency as compared to S3. However, S3 is cheaper as compared to EFS. So this experiment here shows the performance and cost evaluation of S3 versus EFS. What you see here in the left hand side graph is the read and write latency of S3 is constant, and also if you look carefully, EFS performs almost 5 times better while reading the data and at least 2 times better while writing the data as compared to S3. However, the cost of EFS is approximately 10 times the cost of S3. So there is a scope for performance and cost trade-off while choosing S3 and EFS as your storage option. In this experiment, we study the performance of deep reader application when deployed on-prem versus its deployment on AWS Lambda. The server that we used for on-prem deployment had 24 physical cores and 64 GB of main memory. So what we are doing here is we are actually increasing the batch size, which is the concurrent number of images that we are processing on-prem and with the serverless architecture. So as you can see in this graph over here, for smaller batch sizes or low concurrency, we see a linear increase in response time for on-prem deployment. But as the batch size increases or the concurrency level increases, we see an exponential rise in the response time for on-prem deployment. The reason behind this is that when the concurrency is low, the resources that are available on-prem server, those are not utilized fully, they're underutilized. While as we increase the batch size, we see that the resources are saturated and we start seeing the increase in response time. While for the Lambda deployment, as we increase the batch size or as we increase the number of images, we see that the new instances are spawned by the Lambda, and that's why the response time is flat. There is no change in the response time, it's constant. One big drawback of serverless platform is cold start, and cold start latency is due to the time taken by a Lambda instance to prepare the execution environment when the first request arrives. In this experiment, we are looking at the effect of instance configuration on the warm start and the cold start, and also look at the performance and the cost trade-offs for warm and cold start. So what you see in this graph is that as we increase the memory size of the instance from 1.5 GB towards 3 GB, there is hardly any improvement in the execution time or the processing time of the image for warm start as well as for the cold start. But if you look at the cost involved when you increase the memory size, and specifically beyond 2.5 GB, cost increases significantly for both cold start as well as for the warm start. So what we can conclude from this experiment is that in many cases when the memory size is increased beyond certain configuration, there is hardly any gain in terms of the performance, but the cost increases significantly. The recently introduced provision concurrency feature for Lambda keeps functions warm and ready to respond with consistent latency, which is in few milliseconds. And the cold start problem in Lambda function can be mitigated by provisioning the Lambda resources. So based on the expected workload, we provision resources in advance to keep the Lambda instances warm for the expected requests. However, the provisioning Lambda resources results in additional cost, and the provisioning time shall be chosen judiciously to minimize resource idle time. So in this experiment, we are looking at the execution time and the cost incurred when provisioned and non-provisioned resources are used. So what you see here in this graph is that as you increase the concurrency or the workload, in case of provisioned resources, the total execution time is constant. It's independent of the workload. While in case of non-provisioned resources, one, it is always more than the execution time we get with provisioned resources. Two, with increase in the workload, the execution time also increases for the non-provisioned resources. Additionally, what we have observed is that although the cost of provisioning concurrency per unit time per GB data is more as compared to non-provisioned Lambda functions for same memory allocated, but in our case the effective cost using provisioned concurrency is less than the non-provisioned concurrency as shown in this chart over here. This is due to the longer execution time in cold start CTP and Lambda functions. This experiment shows the cumulative processing time on an image, which includes the OCPR and CTP and Lambda function. Now what we see here is that the processing time decreases with more memory allocation to Lambda function, as shown in the graph at the top. Although the rate of decrease in execution time becomes insignificant at higher memory sizes, that is beyond 2 GB, there is hardly any change in the execution time. But what we see here is that the cost of processing increases at the same rate even beyond 2 GB. So this study shows that choosing Lambda configuration judiciously might result in saving cost significantly without compromising the performance. This experiment can help practitioners and researchers in understanding the performance and the cost trade-offs involved. So to conclude, in this work, we have proposed a methodology for migrating an on-prem application which contains large deep learning models and multiple workflows to a serverless architecture on cloud. We have also proposed a deployment architecture using multiple cloud services including S3, EFS and VPC. With the help of our experiments, we have shown the performance and the cost evaluation for the proposed architecture using recently introduced provisioned concurrency feature by AWS. With the help of our experiments, we have shown that when used judiciously, serverless computing delivers high performance with substantial cost reduction.